Hello, today we're going to talk about trigonometric integrals, specifically just trying to figure out what all of the integrals are of our standard 6 trigonometric functions. Remember that since integration is the reverse of differentiation, let's first recall what the derivatives of our 6 functions are. The important thing is that sine and cosine swap roles when we differentiate, with the idea that the cosine adds a negative in front of the sine when I'm differentiating there. And then that's really nice, that means that when I integrate the cosine, I will get the sine, because it's the reversal of the derivative. And when I integrate the sine, I get negative cosine. Again, because that's the reversal of the derivative, I've moved the negative sign from this side of the equation to this side of the equation. However, the other ones are a little bit more tricky. So remember the tangent, its derivative is secant squared. The secant, its derivative is tangent times secant. The cosecant and cotangent are similar to the tangent and secant, except we get a negative sign in front, very similar to how the sine and cosine work. So with these derivatives on the right-hand side, I can see that if I integrate secant squared, I will get tangent. And if I integrate the tangent times the secant, I will get the secant. So these are things where you just really want to memorize what these derivatives are doing, and then if I see the right-hand side, the derivative function, in the integrand, then I know how to reverse it. What's trickier is that we don't have right now the integrals for tangent, secant, cosecant, and cotangent. So let's go through ways of actually producing those integrals and discover what they are. Let's integrate the function tangent x dx. Now, as it stands, we can't do anything because we really don't know anything about the tangent. We know its derivative, but we don't know its integral. And so the first thing we want to do is really convert this into a function of sines and cosines, and that gives us a better feeling for what's going on. If we recall that the tangent is sine over cosine, then we see that this gives us something we can work with. Specifically, this division by cosine is going to be a little bit difficult to work with. However, remember that the derivative of cosine is sine, and therefore we can use u substitution. If I let u be cosine of x, then du is negative sine dx. I don't have a negative sign up here, so I will just negate when I do my substitution. Now that I've done the substitution, I see that I have a nice form for my integral in terms of u, and we know that that's going to be the natural log of the absolute value of u. And as always, when we do substitution, we need to completely replace back into our original variable, so we don't want to see any u's anymore. So let's take that u and replace it with cosine x. And there we are. The integral of tangent is equal to the negative natural log of the absolute value of cosine plus c. And therefore, you can either memorize this pair, but I recommend that if you're ever asked exactly to compute this, that you go through all of these steps instead of just taking it for granted. But there will be some times where you see this as a substep of a larger problem, and therefore you can just plug in the pair. But it might be difficult to remember this formula because it looks really complicated. It looks a lot different than all the derivative formulas because there's this natural log in there. And so keeping in mind that we want to use u substitution, it can help you remember what this formula is. Keeping with the idea that when I put a co in front of something, what I'm going to do is I'm going to switch the role of sine and cosine, and when I do an integration or a differentiation, I'm going to get a negative. That's something to keep in mind. And this is what's happening with the cotangent. It's going to be a very similar formula to the tangent formula, except I lose this negative in front of the natural log, and inside of the absolute value I have a sine x instead of a cosine x. So I would, as an exercise, go through and try this in the similar form as the tangent. Now let's think about integrating the secant of x. Now this one is really difficult. This one is kind of out of left field. It's a little difficult to go through the process. The important thing is if you think about secant in terms of 1 over cosine, it doesn't get you anywhere because you can't use u substitution, and integration by parts is just going to go in an infinite loop. It's going to keep going and going. It's going to never get easier. Instead, let's think about how secant appears inside of a derivative. So remember from my derivative formulas, the derivative of the secant is tangent times secant, and the derivative of tangent is secant squared. So each of these derivatives have a secant involved, and I see that I'm using my secant here. So this is the way that I try to remember this next magic step, which is I'm going to multiply by 1. Now here, I multiplied by 1, but the way I wrote down 1 is very different. I took secant x plus tangent x and divided it by secant x plus tangent x. This is hard to remember, but remember that I'm taking these two pieces, adding them together, and putting them in the numerator and denominator. And the nice thing is what's going to happen is that since I have a tangent times a secant and a secant times a secant here, that's what's going to happen in the numerator. It's going to allow me to use u substitution. Right? So the goal is to use u substitution to get rid of this denominator business, but I need to somehow get my derivatives up in the numerator. Now that I've distributed, we can see that, yes, if I use u substitution here, I'm going to get what I want. And now I see that with this u substitution, I have my nice inverse integral there, integral of du over u, which gives me a natural log formula. Okay. I'm going to keep the substitution here. I'm going to erase a few things, but it's just going to be completing that integral over there. All right, I erased some steps, but I was at this step here, the integration of du over u, which completes the natural log of the absolute value of u. And I'm going to take it to plus c. And now I want to do a replacement of this, u, back to getting my original variable. So completing my substitution, I see that I'm getting the natural log of the absolute value of secant plus tangent, plus c. This one I find to be the hardest to remember, especially the hardest to remember how to do it. So you want to remember how to do this in practice, practice, practice. And to complete our investigation to the 6 standard trigonometric functions, the integration of the cosecant is very similar, except I'm going to put a negative in front of my natural log, and I'm going to use cosecant and cotangent instead of just using secant and tangents. All right? So there's a mapping here that's going on. When I take the co, I'm switching some roles, and I'm adding some negatives. So you can solve this one in a very similar fashion you solve this one. I recommend doing that as an exercise. And then the goal is that you are going to be using these as substeps of larger problems, specifically when we're using higher powers of sines, tangents, cosecants, and such. So get yourself to memorizing these things and also memorizing how to solve them, and then you can use them for harder problems.